Hello everyone, it's Robert here, and today I have a fun little problem for you. 4 lines of code, and your task is to figure out the complexity of this code. Take a few moments, read it, and think about it. Is it big O(n) complexity? Is it n log n? Is it n squared? Or is it something else? I have to admit that the first time when I saw this problem, I quickly jumped to the conclusion that it must be an n squared algorithm. At the end of the day, there are 2 for loops, right? Well, actually it is not n squared. But if you pay careful attention, you will notice that the first for loop is not quite standard. Instead of incrementing by 1, I++, it multiplies by 2 every single time. This changes the problem completely. In the rest of the video, I will work with you to uncover the real complexity of this code. And in the process, we will learn a bunch of techniques and ideas that you can apply to other programming problems. To start off, I want to introduce you to a bunch of mathematical formulas and properties. They're pretty well known, but if you have questions, use the comments area where myself or one of the other viewers will answer your questions. The first property is that log base 2 of 2 is 1. And by the way, from now on, whenever I use logarithms, I will use logarithms in base 2. So I will just say log of n instead of log base 2 of n. The next property is that log of x to the power of y is y times log of x. Another property that we will see later on is that 2 to the power log n is equal to n. This is a property that doesn't involve logarithms, but x to the power p plus 1 is equal to x times x to the power p. And the last property is a sum. 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus so on all the way to 2 to the n is equal to 2 to the power of n minus 1 minus 1. If there is one thing that I want you to take out of this video, is that the complexity of an algorithm is not determined by the number of for loops, but actually by the number of instructions that the computer executes relative to the input size. So what I will focus on is actually counting the number of instructions that are executed on line 4. How many times count plus plus is executed. That will give us the complexity of this algorithm. Let's begin by trying to figure out how many times the exterior for loop is executed. As you can see, I starts at the value 1, then it becomes 2, then 4, then 8, and so on until it becomes to 2 to the power of something. And that 2 to the power of something needs to be just bigger than n. Because we're trying to figure out the complexity of these algorithms, in those cases where the value of n is extremely large, tending sometimes towards infinity, we can approximate 2 to the something to be equal to n. So how many times is the first for loop executed? Well, let me rewrite the values that I takes as powers of 2. We have 2 to the 0, 2 to the 1, 2 to the 2, and so on until we reach 2 to something. It's almost like the powers themselves give us the clue. 0, 1, 2, 3, all the way to something. We therefore have something plus 1 times. That's the number of times the first for is executed, something plus 1. But we still don't know the value of something, so let's calculate it. We can find out based on the relationship that we mentioned earlier. 2 to the something equals n. We apply a logarithm on both sides of the equation, and we get that log of 2 to the something is equal to log of n. Using the second property that we've defined at the beginning of this video, we can determine that the left-hand side of the equation can be reduced to something times log of 2 equals log of n. But log of 2 is 1, so we are reduced to something being equal to log of n. There you go. We found out how many times the first for loop is executed. It's executed log n plus 1 times. Now let's figure out how many times the second for loop is being executed. Notice how j takes the values from 1 all the way to I. That means that the second for loop is dependent on the first one. When I is 1, j will be executed once. When I is 2, the second for loop will be executed twice. When I is 4, it will be executed 4 times, and so on, all the way to 2 to the power of something times. Therefore, the second for loop will be executed in total 1 plus 2 plus 4 plus all the way to 2 to the something times. The value of this sum can be calculated based on property 5 that we've defined at the beginning of the video as 2 to the something plus 1 minus 1. We then use property 4 to reduce this equation to 2 times 2 to the something minus 1. And since something is log of n, we can substitute it and obtain 2 times 2 to the power of log n minus 1. Using property 3 now, we can reduce this further to 2n minus 1. So the number of times the second for loop is executed is 2n minus 1 times. And incidentally, this is also the number of times that the count plus plus on line 4 is also executed. This gives us a total complexity of big O(n), because obviously the constants like 2 and 1 don't count. It might come as a surprise that 2 for loops like these have a total complexity of big O(n), linear complexity. But we can actually test it, because if you notice, this program actually calculates how many times it executes itself. That count on line 4 is literally counting the number of times it's being executed. So we can actually run this program and see if we were right. We're going to run a bunch of tests, and if the value that comes out at the end is roughly equal to n, we know that it's linear complexity. If it turns out that it's roughly equal to n squared, then the complexity is big O(n) squared. So let's test our calculations. The only difference between this code and the one that you've seen earlier is that I took the earlier code and I put it in a function so I can call it multiple times. Let's test it with a few n values and see what comes out. As you can see, for all the values that we've tested, the value in n and the value of the count are roughly equal. Keep in mind that the count doesn't need to be equal to n. It's within the bounds of that constant factor, and that's perfectly fine. The important difference to note is that this is not an n squared complexity. If it would have been an n squared complexity, when n was 1,000, count should have been 1,000,000. But it is not even close. There you go. I hope that you enjoyed this little problem and that you remember from now on that it's not the number of the for loops that counts. It's actually the number of instructions relative to the input size. If you like the video, subscribe, give a like, or use the comments area to drop me a message. See you guys in the next one.